Hello. In today's lab, we will use Newton's law of cooling to determine the time constant of two thermometers. We will work with a common thermometer, which is an alcohol thermometer, and another thermometer, which is a metal thermometer. This is the normal kind of thermometers you use to measure the temperature of turkey when you want to cook it. Well, to begin with, what is Newton's law of cooling? Newton's law of cooling gives us a specific statement on how fast, what is the rate at which a hot object loses heat. In other words, when you turn off this light, this bulb will be very hot, and with time it cools down. Now, what are the factors on which the rate of cooling depends on? What does rate of cooling mean? Well, I'm going to write dq divided by dt. dq divided by dt, the amount of heat lost per second, the rate at which an object loses heat. Now, what are the factors on which it depends on? First of all, it depends on the initial temperature of, well, at whatever time, it depends on the temperature of the cooling object. Because hotter an object, faster will it cool down. Is that right? Yes. Another factor which determines the rate of cooling is the temperature of the surrounding room. In other words, the room temperature. So, if the temperature of this is uppercase T and the temperature of the surrounding is T sub R, then this quantity T minus TR is called the excess temperature. Is that right? T minus TR is the excess temperature. The rate of cooling is directly proportional to the excess temperature. And this is what Newton's law of cooling is. And we can write this equation as dq divided by dt equal to k times T minus TR. Now, this Q, the quantity of heat lost or gained by an object, you know that Q can be written as mc dt. Is that right? Mass times specific heat times the change in temperature. So, if I replace this dq, this Q by this quantity, I can then say d by dt of mc dt equal to, well, I forgot a very small, a minor thing, but a very important one. This is the rate of cooling, means as time increases, the temperature decreases. How will I make that clear in this equation? If with time increasing, the temperature decreases, that has to be indicated by a negative sign. So dq by dt equal to negative k T minus TR. And I'm going to replace my Q by mc dt. So that will be equal to negative k times T minus TR, where T minus TR is the excess temperature. Well, this can now be written as, I'm going to write it in another form, because mass times specific heat is a constant. And I'm going to take it out and divide both sides of the equation. That gives me dt over dt. Now, don't confuse between the uppercase T and the lowercase t. The uppercase T is the temperature. The lowercase t is the time. So dt over dt is negative k over mc T minus TR And this is actually Newton's law of cooling. This is called a differential equation because the left-hand side is a derivative. Now, we are not going to waste time in solving it. I'm going to give you the solution of that equation. And the solution of that equation can be written as T minus TR equal to, that is the dependent variable. T minus TR is the dependent variable. The time is the independent variable. So when you solve for the dependent variable. T minus TR equal to T0 minus TR times e to the power of negative T divided by MC. Well, that's how that equation looked like. T minus TR equal to T0 minus TR e to the power of negative T over MC. And I'm going to replace that MC by another constant. I'm going to write it as tau. And it is this tau that is called the time constant of the thermometer. And our experiment, we will determine the value of tau for each of the thermometers. Okay, let me take it this away. And we have our equation for today's experiment as T minus TR, where T is the temperature of the object at any given time, TR is the temperature of the surrounding room, equal to T0 minus TR. What is T0? T0 is the temperature of the hot object when you start the clock, the initial temperature. In other words, if you put a potato for baking in the oven and you take it out, T0 is the temperature the moment you take it out. Now, this equation is very often used to find the time of death in a homicide. You see, the instant when a person is killed, what is the temperature of the body? The normal human body temperature is about 37 degrees Celsius. Is that right? So this is T0, the initial temperature. And of course TR is the temperature of the surrounding room, the room temperature. Tau is the time constant. Now tell me, if I draw a graph of temperature of the object, I heat an object to a high temperature and allow the temperature to fall. I measure the temperature and draw a graph of temperature against time. Using this equation, tell me how will the graph look like? The temperature will drop exponentially. There you are. That is how the temperature drops. The temperature will drop exponentially. Now, this temperature where the graph cuts the y-axis is T0. Now, let me ask you one thing. Now, in here, look at the rectangle I'm putting in. In here, this time, suppose this time is the same as tau. We are going to define tau equal to, if this t equal to the time constant, then what will this equation look like? So I'm going to say when t equal to tau, the equation becomes t minus tr equal to T0 minus TR times e to the power of, when t equal to tau, this will be tau divided by tau, that is 1, e to the power of negative 1, or t minus tr equal to T0 minus TR divided by E. And therefore, what is this tau? This tau is equal to T under these conditions. You notice that the time constant is a measure, is the time taken for the temperature to drop by how much? By 1 over E of the original value. You see, T0 minus TR is the original excess temperature. And this is the excess temperature after a time T equal to tau. So the time constant is a measure of the time taken for the excess temperature to fall by how much? By 1 over E of the original temperature. So, in order to find the time constant tau, what all we need to do is, we start with the original temperature T0. What is the temperature when you start the clock? That is your T0. Now, find the time taken for this temperature to fall by 1 over E of T0. What is the time taken for the temperature to become T0 divided by E? In other words, 1 over E is approximately 0.37. So the time taken for this temperature to fall to 0.37 of T0. That is your time constant. So once you draw a graph like this, and suppose, I'm going to give you a simple value. Suppose your T0 equal to 100 degrees Celsius. Now, how do you find the time constant for this thermometer? The time constant tau will be or is defined as the time taken for this temperature to fall by 0.37 of that T0. Now, 0.37 of 100 is 37. And suppose this is 37 degrees Celsius. Once you have obtained your graph, what all you need to do is draw a horizontal line that touches the graph from 37 degrees, that is 0.37 of the original temperature, and then draw a vertical line to touch the time axis. This time will be a measure of the tau. That is one way to find the tau. So, you will draw a graph of temperature against time and measure the time taken for the initial temperature to drop to 0.37 of the initial temperature, and that will be the time constant. That is one way to measure the time constant. There is, however, another way to measure the time constant, and that is, I can write this equation. If you take the natural logarithm of both sides of that equation, let me do that. If you take the natural logarithm of the two sides of the equation can be written as ln of t minus tr equal to ln of t0 minus tr minus t over tau. Alright? If you take the natural logarithm of that equation, this is what you get. Now, what are the variables in this equation? If you notice that the variables are the temperature of the hot object. This is a variable. The room temperature is a constant. The initial temperature of the object is a constant. And the other variable is the time. So one variable is time, that is the independent variable. Is that right? Well, and the other variable is the temperature. Now, if I write this equation like this, look at this. ln of t minus tr equal to negative t over tau plus ln t minus tr ln t0 minus tr. So ln t minus tr equal to negative t over tau plus ln t0 plus minus tr. Now, this is an equation of the form y equal to mx plus b. Look at this. This is your x. If you now draw a graph of, what will be on the y-axis? ln of t minus tr on the y-axis, and the time on the x-axis. The graph will be a straight line like this. Why is it like this? Because the slope is a constant. Is negative. What will be the slope of this equal to? Will be negative 1 over tau. So, if you now draw a graph of ln t minus tr against time and measure its slope, you get the reciprocal of the time constant. That means you can get two values of the time constant by drawing these two types of graph. The first graph is the temperature against time, and we use that graph to measure the time taken by the initial temperature to fall by 0.37 of its initial value, and that is a measure of the time constant. Also, by drawing a graph of ln t minus tr against time and measuring the slope of that graph, you get the reciprocal of the time constant. So obtain two values of the time constant and obtain a percent difference. That means when you do that for two different thermometers, there will be two graphs for each. So you will have 4 graphs altogether. Okay? Before taking measurements, please make sure that you have the stopwatch on the video. Well, we're going to measure temperature in intervals of time. So that means your stopwatch must be ready for you. Well, we will start with the metal thermometer, and if you notice, it is marked in degrees Fahrenheit. So you need to measure these in Fahrenheit and then convert it to degrees Celsius. I have given you the conversion equation in the lab manual. All right? I hope you can actually see the readings well. All right? Try and make the readings as accurate as you can. Okay? Try to read up to 1 decimal if you can. Well, what I'm going to do is I'm going to heat the metal stem of the thermometer. Then the pointer will come and cross this 220. I'm going to take it well above there. And when the pointer comes back to 220, that is your 0 of time. All right? Start the clock when the pointer comes back to 220. And then measure the temperature every 5 seconds. All right? I'm going to repeat it. Measure the temperature every 5 seconds, because the temperature is going to fall very fast in the beginning. So for the first 1 minute or so, measure the temperature every 5 seconds. And then on, measure the temperature every 10 seconds. Okay? I don't think I need to repeat that. When the pointer comes to 220, start your stopwatch. That's your time 0. Take the temperature after 5 seconds. Take it again after 10 seconds. Take it again after 15 seconds, and so on. Take the temperature every 5 seconds for the first 1 minute, and then take the temperature every 10 minutes. Okay, let's start. Alright, I have heated it, and now when the pointer comes to 220, start your clock. And then measure temperature every 5 seconds. Well, I think you can stop now. The temperature reached about 72. It's coming very close to the room temperature, and now that should be enough. Now I have the second thermometer. It is actually in boiling water. The moment I take it out of the boiling water, I will focus the camera onto it and I will say ready. And when I say go, you must start your clock. You may not be able to see the thermometer then, but start the clock when I say go, and then measure the temperature every 5 seconds. All right, ready? All right, get ready. I'm going to lift it when I say go. You start your clock. All right, go. Well, I think you can stop measurement now. All right, you have sufficient time, temperature readings. I hope you got the first few readings every 5 seconds. They are crucial. Okay, I'm sure you are now ready to deal with the data you have, but you need one more information, that is the room temperature. Is that right? I will give you the room temperature. The room temperature T sub R is 22 degrees Celsius. Okay, so complete your tabulations for both thermometers, time against temperature. Draw these two graphs for each thermometers. Find the time constants from each. Find the percent difference. Answer the questions. Well, let me show you a good way to put this equation into use. Now, this is an important and useful equation in forensic science. For example, suppose a murder was detected and you need to find the time of death. A dead body was detected in a room which kept a constant temperature of T equal to, let's say, 20 degrees Celsius. The temperature of the room where the body was found was 20 degrees Celsius. And of course, for a human body, the initial temperature will be about 37, well, let's take it 40 degrees Celsius. All right, the initial temperature of the body is 40 degrees Celsius, and the room temperature is 20 degrees Celsius. Well, on a second thought, I don't think you should use 40 degrees, because 40 degrees, that man would have been very sick and very feverish, so it may not be a murder. He must have been died of very high fever. So let's go back to our 37 degrees. That is the temperature of a healthy human being. So at the time of death, when time is 0, the temperature was 37 degrees. And suppose the police came in around 5 p.m. and they measured the temperature. They measured the temperature, I'm going to call it T1, and they found the temperature was 34.2 degrees Celsius. So they came a little sometime after the murder was committed. So they came at 5 p.m., measured the temperature at 34.2 degrees Celsius. Now, they came back after 4 hours. That means they came back at 9 p.m. and they measured the temperature again, and they found the temperature was 25.8 degrees Celsius. Okay. Well, let's not give that much of a time. They came at 8 p.m., 3 hours later. Okay? Now, can you use these two data to find the time of death? Using that equation. Well, if you want to find the time of death, let's say the death occurred T seconds, all right? Let's say T hour. Death occurred T hours before 5 p.m. That's right. The death occurred T hours before 5 p.m. That means if you now use this temperature here, okay, you know TR, you know T0, and you know TR, then this T will be the time of death, because that T is the time 3 hours before 5 p.m. So let's put those quantities in that equation. What will that equation be like? It will become, the measured temperature is 34.2 minus TR is 22 will be equal to 37 minus 22 times e to the power negative t over tau. You got now one equation that contains two variables. Well, you cannot find the value of this time if you don't know the value of tau. And that is where we now use the second equation. The police came 3 hours later. That means 3 hours later means when they come, the time is t plus 3 hours. And what is the temperature then? It is 25.8. So we now replace this t by 25.8. 25.8 minus 22 equal to 37 minus 22 e to the power negative t plus 3 divided by tau. 3 hours later, this is the temperature. Okay, now I'm going to leave it for you to solve these two equations. I want you to use these two equations and solve for that time. That time t is the number of hours before 5 o'clock, and that will give you the time of death. Alright, I want to see how many of you will solve that equation correctly. Well, that is a good lab. Alright, take some time and do a good write-up and tell me what is wrong with the method. Is there anything wrong with the method that we used in using Newton's law of cooling? As I told you some time ago, that your thinking and your analysis of the experiment is very important for me because I am your partner. So you got to tell me, is there anything I could have done better to improve the experiment? Okay, I will see you for the next lab later on.